Nakhmani. How are you? Questions on the previous lectures, homeworks. I plan to publish another homework soon, hopefully this week, another lab as well for all the topics that we covered so far. Probably will be more business topics to more reflection-based topics and less of the theory-based topics. And today it will be big of the abstract topic, linear spaces. This is the most complicated and abstract topic in linear algebra. And hopefully after that, it will go to all of the practical topics because you will learn all of the important theoretical stuff, and then we can get to actual practical stuff, how we can apply all of that. Let's see. Okay. No more questions about homeworks, labs, lectures, like that. Okay, so what is the motivation to use that type of abstract things in linear algebra in general and in applications in general? Wow. So we are looking for something which is unifying structure for all of the linear algebra, practically speaking. Something that would generalize to almost everything and anything in linear algebra and applications as well. And most of the applications that you maybe learned from different topics and different places related to signals or related to circuits or related to analysis of different things or maybe imaging or maybe, I don't know, controls. All of that is coming practically from the same source. Okay, so you can generalize all of that and to have single unifying theory of everything in linear algebra, typically speaking. And this everything is linear spaces that we'll be talking about today. So in linear spaces, you can unify Fourier transforms, Laplace transforms, Hilbert transforms, Gabor spectrograms transforms, and other integral transforms in general. And you have many of them. So if you have any experience, you don't have to know any of them. But if you have some experience with any kind of transforms, most of them are coming from the same formula. You have same formula, and the idea of that formula is orthogonal projection in linear subspace. So all of them just projecting into different linear subspaces. This all of these transforms. Typically in courses you learn them as, oh, here is a formula. They take the formula, applies it to signals, and you will get some interesting new information about the signal. That's how you learn it in signals and systems typically. They give you integral of whatever Fourier transform with exponent, blah, 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 or cosine and sine. It's coming from nowhere. Like, why would you choose that thing? This is not clear at all, like where it is coming from. So this is where it is coming from, linear spaces. It's just projection on particular specific linear spaces, all of these transforms, okay? And you can invent your own transforms if you want to. More than that, it's not only transforms, it's also all of the sampling theory and many other things. Like if you heard about like Nyquist frequency and like Nyquist-Shannon sampling theorem, how you sample different signals in time, and then reconstructing back the signal with sinc function, just sine divided by t, like sine of pi t divided by pi t. It's like reconstruction of signal. It's all coming from the same formula, same thing. If you just substitute particular kernel functions with some specific function, you get all the theorems together, and you can prove them all together based on that theory. So it's practically speaking generalization of everything we learned so far, and we will get to that. It's not simple. I'm not expecting you to get all of it easily. I'm not even hoping that you will remember all of these details of axioms and theorems and the spaces and connections between different parts. It just, you need to be aware that it exists. When you need it, you will look it up, okay? So you will see where it is coming from, and it will give you some sort of motivational thing about where things are coming from, like what is the reason for people to define one type of functions as kernel and not some other types of functions. For example, like why Fourier defined specifically sine and cosine as the function, as like main function in the expansion, and not, I don't know, x squared and x cubed. Like, what's wrong with them? Like, isn't that the same thing? Like, you can pick any function you want. No, not really. I mean, you can, but not really. You have limitations which you will see from here, from that theory, why it is that different. And this is because of the orthogonality of different functions, perpendicular type of functions. And we will define what is orthogonal functions in general, because this is, again, coming from linear algebra of infinitely dimensional spaces, which is a little bit more tricky than finite dimensional spaces. But ideas are the same ideas like linear algebra, regular linear algebra, okay? Additional things that you can do, you can generalize it to wavelets, Will distributions, adaptive spectrograms, all kind of other representations in spectral analysis that people are using frequently for multiple different purposes. Now, not all of them are orthogonal. This is the thing. So Fourier transforms, like cosine is orthogonal to sine, things of that kind. With wavelets, it's over complete basis, which means that you have more functions in wavelets than you actually need to be orthogonal. They are not orthogonal to each other. So you have some sort of overlap. When functions are not orthogonal, the projections overlap. So you have additional components in your representation of signals or systems or whatever you're using it for. So this is a little bit different, but again, coming from the same formula, same idea. Just projection, which is not orthogonal, okay? This is wavelets and other things with wavelets. And again, wavelets probably is the most popular tool after spectrograms to investigate any kind of signals. Wavelets are used everywhere in engineering, and people just use it to see spectral distribution of frequencies in wavelets, wavelet scalograms. So spectrograms in wavelets are called scalograms because this is about scales. They are kind of scaling signals. And next semester, I will have an entire course on what I will just touch here. Okay, so I will just give you a glimpse into the theory of signal analysis in general and generalizations. And I will devote the entire course to that single lecture practically, explaining more details and getting into more applications and getting into actual MATLAB code, which is doing all of this frequency analysis stuff on any kind of medical, biomedical signals or any signals. It doesn't matter. I mean, theory is same theory. It's not really different. Okay. Any questions on that? So these are non-orthogonal projections. Okay, so this is motivation for why we need all of the spaces. We will see a few examples of how you use the spaces, how you project into the spaces, how you can clean noise if you want with the spaces, and a few other applications of, but probably later this week, not today. But now we will start with the theoretical part. So first of all, how we define linear space. You define it by two properties and multiple different axioms. If you remember, we had two ways to generalize things in math in general. It's not only linear algebra. Mathematicians are doing that all the time. They say, oh, I see some pattern. Let me extend the pattern and generalize it to more dimensions, to more whatever. Okay, just bigger and nicer type of thing. Or simplify it. So starting with something very complex, let me simplify that. Something more beautiful, mathematical. So something more elegant representation. So notation here is very important. If you're using good notation, it's easier to represent things in more elegant way. Let's say instead of using that big table of numbers, you can write letter A to represent that entire big table, which is matrix, okay? And then you can manipulate matrices and solving writing system of equations like AX equals B instead of writing all of this A11 times X1 plus blah, blah, blah. Like huge notation problem where you need to write it every single time and you're doing that all the time. So it's a problem, okay? It's time-consuming and not very intuitive what it means. But when you manipulate matrices, and instead of doing all of that Gaussian elimination, you're saying like A inverse. That's it. This is what that thing is. Okay. So just symbolically, it's much more elegant to write that kind of things, and you can see that entire thing immediately, like what it does, instead of doing that entire process. And behind the scenes, it's the same process. Okay, you're not changing the process, but just notation is important here. So notation of linear spaces is a little bit complicated and has, again, a lot of definitions, terms, other things. I do not expect you to remember all of these details of all of these definitions, kernel spaces, column spaces, row spaces, tons of them. But try to get the overall idea, okay? This is what's important here. So that way to define linear spaces is coming from, let me figure out some common properties among multiple different things. And these properties will define what I will call linear spaces. This is the way mathematicians do that, okay? So they will define particular axioms. So something needs to work on some objects. Some rules need to work on these objects, like in algebra. You have these axioms of algebra. They need to work on these objects. If any kind of object satisfies these rules, I will call them that thing that I define by these rules, okay? So here I'm defining these properties, okay? And you have tons of them to define linear spaces, but we will see how it simplifies to very simple things. So we will stick to very concrete examples of linear spaces. We will not like take any linear spaces. We will work mainly with a few specific linear spaces. So on the next slide, like don't worry, you will have here many different properties. On the next slide, we will stick to particular things which are linear spaces. So you will understand a little bit like where it is coming from, the generalization of linear spaces. So it needs to satisfy two things. It needs to be closed regarding addition. Remember what is closed in algebra? Operators which are closed with regard to particular, like closed with regard to particular operation in algebra. It means that if you're taking two things from a particular set, you're combining them with that operation, whatever that operation is, you get another thing in the same set, always. So no matter which two things you pick from that set, you combine them together somehow. It could be add, addition, multiplication, whatever the function is, or union, or intersection, or whatever. Like some operation on two things from the set, two objects. That combination of them will be still in the same set. This means the operation is closed. Okay, you get exactly the same thing in that set. So this is what vector addition means here. So if you're taking two objects, which are called vectors in that sense, and these are not necessarily linear algebra vectors, which is just a bunch of numbers, but could be any kind of other vectors. We will define what that means later. So if you're taking these two objects from particular space, particular set V, okay, and then you can define operator which is called sum between them, and the sum will be still in the same set, which is kind of closed operation, all right, regarding addition. So addition belongs to the same set. So if you're adding two objects from the same set, you get objects in the same set. And scalar multiplication. If you multiply that object from that set by scalar, you get object in the same set. Okay, so it's closed with regard to multiplication by a scalar. These are two properties that we need, okay? So it will satisfy all kind of axioms, and then we will call it linear vector space, or just vector space. So let's say we have these three elements of the vectors, x, y, and z, and we have some scalars, alpha and beta, okay? And we have axiom number one, it's associativity of addition, which means doesn't matter where I put the parentheses, it's still equal, okay? So associativity property. Second one, you have some sort of zero vector, whatever it is. Zero vector means, it is how it is defined, that if you add it, and again, you have function of add, and add might mean all kind of things in algebra, in abstract algebra, okay? So if you're adding that vector zero to any vector, you get back that same vector. Okay, this is what it means. Third axiom, negative vector exists, which means you can define in that same set V, you can define some other vector that if you add these two vectors, you get zero vector. Okay, so it's kind of negative of that vector, practically speaking, okay? And the last addition axiom is that you can switch the order of addition. The order of addition doesn't matter. X plus y equals y plus x. And these are 4 axioms for addition for the vectors. Now you have multiplication by scalar type of axioms. First of all, if you multiply this distributivity from regular algebra, if you multiply number by sum of vectors, it's number by the first vector plus number by the second vector, distributivity. Second axiom is the distributivity of the scalars, which is almost obvious because, but not that obvious, it's still axiom, okay? Axiom means obvious, almost translated as obvious. So alpha plus beta is still distributivity, alpha plus beta, which is sum of two numbers times some vector. It's first number times vector plus second number times vector, okay? Third axiom is commutativity, associativity of multiplication by scalars. So if you have two scalars multiplied by x, you can put parentheses wherever you want. You can switch order of scalars, and you can do whatever you want with that. All right. And the last one, there is such a multiplication by 1, which is not changing the vector. Okay. So if you multiply by 1 any of the vectors, the vector will not change. And as you can see, this obviously works on regular vectors. All of these properties obviously work on all of the vectors that we have in linear algebra, which are just regular vectors, right? X1, X2, X3, X4, and so on. All of this bunch of numbers in a column. All of these properties obviously satisfy any of the regular algebra, right? If you're talking about numbers. So numbers are also linear spaces in a sense. So if you're talking about like R, which is all of the real numbers, this is linear space, okay? That's set. But you can put multiple numbers and vectors, but you have much more than that, and this is the main thing. So first of all of the complex vectors are also satisfying the same thing, because you don't have anything related to multiplication or conjugate of vectors or matrices or anything like that. So all these properties work both for complex vectors and real vectors. But how about polynomial space? All of the polynomials, like look at these properties here. So if you're taking one polynomial plus another polynomial plus third polynomial, you can add them in any order you want, right? It doesn't matter. You can put parentheses, like combining first two polynomials or second and third polynomial or first and third polynomial. It doesn't matter. You'll have same sum, same polynomial if you add in 3 polynomials, right? Obviously, you have 0 polynomial, which is just number 0. This is 0 polynomial. If you're adding 0 to any polynomial, you get same polynomial. Nothing changes. You have negative polynomial if all of the coefficients of your polynomial are minus coefficients of your given polynomial, and you add in these two polynomials, you get 0 polynomial, which is 0 number at that case, okay? And you can switch the order of the polynomials. In addition, if you multiply constant by polynomial, you get each coefficient multiplied by that polynomial. So if you add in two polynomials, each one of their coefficients will be multiplied by the same constant, right? So all of these properties work for polynomials of any degree, okay? But you can talk also about polynomials less than nth degree, less or equal to nth degree, okay? Let's say up to quadratic polynomial, up to second degree, all right? So all of these polynomials also will satisfy all of these rules because it's kind of subset of the previous set. And always, if you add into polynomials of quadratic degree, you cannot get something of higher degree, right? If you multiply by a constant, you cannot get polynomial of higher degree. You can get lower degree, like some of the coefficients might be 0, right? So quadratic coefficient also might be 0. So you can get to lower degrees, but not higher degrees when you're adding or multiplying by a scalar of polynomials, right? So this will satisfy the same kind of properties And polynomials are like that. How about matrices? All of the matrices, you can think about that as just all of these elements in the matrix is like one vector. And since you're doing all of these manipulations point by point, which is like element by element, you also will have same properties of regular algebra, all right? So these are the main spaces that we care about, but you have many more than that, all right? So we will talk about matrices, we will talk about regular vectors, complex or real, we will talk about polynomials, and later we will talk also about functions, which will be infinitely dimensional space, Hilbert space, continuous functions, and they will be kind of vectors where you have infinite number of points, practically speaking. So we will be thinking about that as like super long vector, infinitely long vector of values of function at each particular real point. Okay, it's like infinite number of points, and this will be the continuous function. And they will satisfy same thing if you're looking on these properties and take any function f of x and f of y, okay? You can combine them in any order. You can switch the order of the functions when you're adding functions. If you multiply a scalar by a function, each function will be multiplied separately by the same scalar. So it's like same thing. Okay, all of these properties work for any function, practically speaking. So they also linear spaces or continuous functions. Okay. Any questions so far? So these are most important things for us. Yes.
Can you go back to the previous slide? I'm kind of getting confused. If we say x, y, and a,
Alpha and beta, yes.
what are they? Are they vectors? Are they numbers? Are they?
So alpha and beta, they are complex numbers or real numbers, just numbers, scalars. Okay, scalars are numbers. So alpha and beta are numbers. X, Y, Z are vectors.
Vectors.
Yes. So we always use X, Y, Z for vectors and alpha, beta, gamma, all the Greek letters for numbers. Okay. Any other questions? All right. So linear combination is one of the main things in linear algebra, and we're using that everywhere. And the ideas that I discussed in the motivation will come from that definition, what is linear combination of things. And you can think about linear combination as weighted average of multiple vectors, okay? So it's defined very simply by multiplication of some coefficients by some vectors, and you're adding them together, like that. And this is main building block in linear algebra. So if you have vectors v1, v2, v3, v4, and so on, up to vm, linear combination is defined as some constant times v1 plus another constant times v2 plus another constant times v3, and so on until you get to the last vector. So this is linear combination, and this will be scalars, which is just numbers, and they could be practically everything I say about C will work also with R, because R is subset of C. Okay, like real numbers are subset of complex numbers. So I'm generalizing that immediately to C, that works with C, but you can think about R as well. Okay, so it could be R or C. And here is a simple example of that. Let's say you have vectors v1, v2, and v3. You want linear combination of these vectors. Linear combination will be of the same dimension always as the original vectors. And you can combine them only if they are of the same dimension. So all of them, in that case, are 2 by 1 dimension, right? There's like 2 vectors. It's 1, 2, 2, 3, and 3, 4. So if you're doing alpha 1 times 1, 2, plus alpha 2, 2, 3, plus alpha 3, 3, 4, you get just alpha 1 times 1, plus alpha 2 times 2, plus alpha 3 times 3. So you get the first row, which is the first element of that vector, and this will be some number, okay? And same thing with the bottom one when you multiply by the bottom numbers. So this is again vector 2 by 1, and this linear combination of these 3 vectors. And here is the most important thing that people are doing in linear algebra, like why we are going all of that way together with solving system of linear equations. It's expressing a vector as a linear combination of other vectors. Okay, so you choose particular vectors, and you want to write that vector as that linear combination of other vectors. And we've seen usability of that type of approach already with multiplication of two matrices, like decompositions like LU, for example, or Q, decomposition, QR, decomposition, okay? So you can write one matrix as multiplication of two other matrices, and this gives you some benefit because this matrix is kind of easily identifiable, or you can work with them easily because they're triangular, for example, or orthogonal, or some other nice property, okay? So decomposition in linear algebra is a key idea, how to write something as a function of something simpler. So this is one of the main ideas of linear algebra, key ideas, I would say, which is describing that you can write any vector as a linear combination of some particular other vectors. And if these vectors have some nice property, this distribution will be very easy to manipulate or to understand or to have some intuition about like what that vector is in terms of these other vectors, okay? We will see some ideas like how you do that a little bit later, and probably a few weeks we'll be talking about these applications of how you can use that same rule for everything, that you're just writing something as a function of something else. And for us, it will be like you can think about it intuitively as transforming system of coordinates. So some system of coordinates are not very convenient. They are not aligned with different data points or whatever. So if you rotate it, scale it, and manipulate it a little bit, maybe it will be aligned with a bunch of points that you need to describe, or this is how PCA, by the way, works, principal component analysis. We will talk about that later. So you have many, many different applications of that idea. And all of the integral transforms are based on that idea, how to write particular data point as sum of frequency components as example. And these frequency components will be cosine, sine, and other things in Fourier, or exponent to minus st in Laplace, or whatever other basis functions are. We will see all of that a little bit later, all right? So here's the idea. You want to write vector x, whatever that vector is, as linear combination of other vectors. Sometimes you can do that, sometimes you can't. So if vector x can be written as that linear combination of these other vectors, sometimes you have only single solution, which means only one way to write it, and sometimes you have infinite number of possible solutions. There is never like 2 solutions or 5 solutions. It's either one solution or infinite number of solutions, or no solution. These are the options, like almost everything in linear algebra, and this is clearly coming from solving system of linear equations, okay? Where you can have only one solution, which is matrix A will be invertible, and then you have one solution, which is that inverse A times B, solving system of equations. Or it will have infinite number of solutions, which means that multiple equations in your system of equations has kind of free variables that you can choose whatever that variable is, and then all other variables will be written as a function of that free variable, unconnected variable, okay? So this is like infinite number of solutions. Or you have contradicting equations. And if you have contradicting equations, then you have no solution to it. And we will see how to overcome that problem with least squares later, which you'll find the closest solution, but not exact solution. But there is no exact solution in these cases, okay? So for a given x, we want to find coefficients alpha I in that linear combination for the equality to be true. This is the idea. To do that, this is practically solving linear system of equations, because alpha 1 times v1 plus blah, blah, this will be just vector, okay, with all these coefficients as variables. So on the one side, you will have just numbers, which is that vector x that you want to represent. On the other side, you will have equations with alpha 1, alpha 2, alpha 3, whatever the number of alphas you have them, all right? So it will be practically comparing these two vectors. It's solving system of equations. This is what it is. So here is an example. Let's say you want to represent particular vectors, and you have v1 equals 1, 2, v2 equals 2, 3, and your x that you want to represent is 1 and 2. So here the answer is obvious. You don't need to solve any system of equations. It's just one of the first kind plus 0 of the second kind, because the vector that you want to represent is already the first vector that you have, all right? Now, how about another vector, 5 and 7? You want to represent with the same x1 and x2. So these are your vectors that you want to write it. So 5 and 7 could be written as alpha 1 plus 2a2 and 2a1 plus 3a2, which is that linear combination, which is alpha 1 times this vector plus alpha 2 times this vector. Okay, so this will be that thing. Is it clear where this thing is coming from? Okay, so this is just first vector, which is 1 times alpha 1 plus 2 times alpha 2, and bottom part is 2 times alpha 1 plus 3 times alpha 2. Okay, and this equals to that vector. You solve that system of equations, which is that first equation and second equation, and then you get these two coefficients. This is representation, so it's like -1 times the first vector plus 3 times the second vector will give you 5, 7. You can check them. Take -1 times 1 plus 3 times 2 should be that number, okay, and so on. Now, what would be the most convenient vectors to be represented in? This is called standard basis. Have you heard about standard basis for vectors? So these are very, very simple vectors. These vectors look like that. You have 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, and so on. Okay, so it's like 1 at J's place, okay? And 1 is kind of moving to the bottom, and the last vector will be 0, 0, 0, 0, and 1. Okay? This is standard basis for everything. So if you try to represent any kind of vector in Z using this type of vectors, which are, by the way, called with letter E, okay, or whatever, elementary vectors, okay, they are called elementary, letter E, like E1, E2, E3, and so on. So if you represent any vector using elementary vectors, E1, E2, E3, and so on, what would be the answer? What would be the coefficients? Alpha 1, alpha 2, and alpha 3. Do you understand the question? Like you have vectors like that. E1 equals 1, 0, 0. E2 equals 0, 1, 0, 0. So on until we get En equals 0, 0, 1. Okay, these are elementary vectors. Okay. Now you want to represent vector x, which is whatever x1 through xn as alpha 1 e1 plus alpha n en. So what would be these numbers? Alpha 1, 2, 3, 4, 5, and so on.
That's whatever is in X. Yeah, because
They will be just equal to these numbers. These are alpha 1, alpha 2, alpha 3, so on. So these are coordinates of the vector. So if you're representing any vector in that, we'll call it basis in a minute, okay? You're just giving coordinates of the vector, which is vector itself. Okay, so your coefficients in linear representation, this will be coordinates of that vector, which are elements of that vector. And this is why we interchangeably call many times coordinates and elements of the vector. Same thing. Because we're thinking typically about that type of standard basis. Now, if you're changing that to something else, you can think about that as representing that vector in different system of coordinates. Because look, what is that? Like think about 2 dimensions. You have this vector and this vector. What is that? This is just that system of coordinates is 1 and 1, right? So this is the first vector, x vector, y vector. How about 3 dimensions? Same thing, you have 1, 0, 0, which will be like let's say this is X, Y, Z type of thing. So you have one in that dimension. This is first vector, second vector, third vector. Okay. Regular rectangular system of coordinates. This is what that thing is. Okay. But if you're using different vectors, you represent that vector. You're practically representing that vector in different system of coordinates. Okay. Then you have other vectors. And it would be very convenient to represent it if the system of coordinates is orthogonal, and not very convenient if it is not orthogonal. Okay, so if some of these angles are smaller than 90 degrees, then you have kind of problem. You have overlap between what this axis is telling you regarding the coordinates of that thing and that axis, because they kind of overlap in the information that they provide. Okay, and it's difficult to split that information into two different things. And this is why we love transforms which are orthogonal and struggle a little bit with transforms which are not orthogonal. Okay, this is where the difficulty is coming from. Because representing numbers or vectors in rectangular systems of coordinates, much easier. Most of the things will disappear, cancel out, and so on. Okay? Try it again. Any questions so far? All right, another term, span. It's all connected to the same linear combinations and so on. So vector space is spanned by vectors v1 through vm. If any vector in that space could be written as linear combination of that type of vectors, okay? So you can take linear combination of some given vectors. If you can represent any vector in particular space using that linear combination, then this is called span, spanning set of vectors, okay? And typically we will be looking for minimal spanning set, because let's say if you're taking all the vectors in V, definitely all vectors will be represented by these vectors, right? You have like infinite set, all of the vectors are included, each vector is representative of itself, and everything else multiplied by 0, so you don't care. So this is easy, but we are looking what is the subset of V, of vectors, that will represent all of the vectors as linear combination of themselves in that set V. This will be called basis, okay? This is a minimal subset of V, which is spanning the entire linear space, V, all right? This is the overall idea, that you will be able to represent with only few vectors all of the vectors of interest, all right? And this will be useful for multiple different things, like you have eigenfaces as example, recognition of faces type of idea, where you don't need to know all of the faces that people might have, but you need to have only subset of faces by combining which you can generate any other face or close enough. This will be the overall idea of the eigenfaces thing, okay? So here is an example with a standard basis. So R3 is obviously spanned by standard basis of that space. So if you're taking all of the orthogonal coordinates, coordinate system, regular rectangular coordinate system like that, and you have vectors E1, E2, and E3, it will span entire space. So you can write any vector as linear combination of these three. This is as elementary as this part, okay? Just alpha will be the vector itself. So you can write any vector and you even know what the answer will be, okay? These are the elements of your vector X. But you cannot do the same thing with E1, E2, and some other vector like that, let's say. Why is that? So if you're taking like 1, 0, 0, 0, 1, 0, 2, 3, 0, you cannot write every vector. Like what vector you cannot write as example? You cannot write E3 with combination of these two vectors. Why is that?
Well, the vector in the third dimension is 0, So you can't scale it to
It's not dimension, it's like value. The third value, third element is 0. No matter what constant you multiply by 0, you still get 0. So combination of two zeros, which will be like alpha 1 times 0 plus alpha 2 times 0 plus alpha 3 times 0, it still will be 0. No matter what you do, you cannot get the third element in the vector. It always will be 0 from any linear combination of any of these three vectors, okay? So if you're taking E1, E2, and 2, 3, 0, linear combination will always end with 0 at the bottom, okay? So any vector which is not ending with 0, you cannot represent it with any combination of these vectors, all right? So it's impossible. So this is not spanning R3. Okay. Polynomials of up to second order could be spanned by these three polynomials. You can write any polynomial, and this is also, by the way, standard basis of polynomials, up to second order, and S1, t, and t squared. These are the functions that you choose to represent any polynomial. So if you're taking alpha 1 times 1 plus alpha 2 times t plus alpha 3 times t squared, practically you can represent the same polynomial. And why it is standard basis? Because coefficients of that polynomial will be that alpha 1, alpha 2, and alpha 3 by definition, right? Is it clear what I'm saying? So coefficients of the polynomial with that standard basis will be your answers to coefficients of the linear combination of these three things to write any quadratic polynomial or first order polynomial or any other polynomial up to second order. How about that? So any polynomial up to degree n could be written using 5t minus 5 squared, and so on. And by the way, 5 is just a random number. You can choose any other number if you want. Like if it would be like 1, t minus 1, t minus 1 squared, and so you can use any other number. Okay, 5 is just as example. All right. So you can write any polynomial of order up to n using combination of these things. All right, and you can show that. It's more difficult to show. It's not that trivial to show, but you have all kind of vectors using which you can represent your polynomials, and representing them in particular basis using particular polynomials of that kind. Okay, is very important because you want them to have particular properties. For example, you want t not to be equal to 5 in that particular example, okay? So you're looking for properties like how close the roots of the polynomial are to 5. Simple example, right? So you have a bunch of polynomials, all possible polynomials that you maybe eject from your question or problems that you're solving. So you fit in some functions, some polynomials, and these polynomials having some roots. You want to know where these roots are. Computing roots is complicated, especially when you have no analytical solutions for it, and only numerical solutions, iterative solutions. But you care to represent, all you care is like, will you have root of 5? So all of these polynomials, except number 5, will have root at 5. So no matter what coefficients you choose, you should get the number 5 times constant, right? If you have root. If you do not have root at 5, then all of these coefficients will not be 0, right? Do you see where I'm going with that? So if you're representing in system of coordinates and your coordinates are these functions of t, it should be 0 everywhere. And only on the first axis it should have some value. Then you have root at 5. You don't need to compute anything if you represent it that way. Okay, you don't compute any roots. This just gives you different information about your polynomial that you represent using that basis. Again, depends on the problems that you're solving. So this gives you different insight into what it means, right? So this gives you kind of thinking mechanism. How about matrices? This is a standard basis for matrices. You have one in particular ij element. Okay, so Eij equals to that 1 and 0 everywhere else. This is a standard basis for matrices. And again, in that basis of matrices, elements themselves of the matrix are the coefficients that you multiply these things by. Okay, but you can have other matrices which would give you different system of coordinates to represent particular matrix. So you can write matrix as sum of other matrices, linear combination of other matrices. So these are examples. Any questions? Okay, subspace is just part of space. It's still linear space, which is subset of another linear space, and it's called subspace. Okay, it's just another linear space, but it's part of another space. So bigger space will be called V, subspace will be called W, typically, and you don't need for subspaces to check all of these properties that we mentioned before. You remember you have 4 addition properties and 4 multiplication by scalar properties. You don't need most of it, okay? Why? Because you know that this is already a subset of linear space. So most of these properties are automatically working, all right? So if you just need to check if something is subspace, and you know that it is already a subset of something else, you need particular properties to check. Property number 1, that 0 vector belongs to that subspace. All subspaces include 0. All right, this is property number 1. Property number 2, it's closed with regard to addition. This was the first axiom, if you remember, in the addition axioms, okay? So you need to check only that one. That if you're taking 2 vectors from that W, adding them together, you still get something in W. Because this might not always be the case if you're taking only piece of V and not entire V. Okay, for V, it's true. But for W, which is part of it, might not always be true. Maybe it's like jumping into V, but not in W. So then it will not be subspace. So addition should sit still in that subspace. Now, third property actually includes the first property, and I will explain why I have that as 3 separate properties. The third property is that alpha times x, which is number times vector, will still need to be in that subspace. Okay, so it's closed with regard to multiplication by scalar. Now, obviously, if alpha equals to 0, so 0 will belong to W, right? So this is first property. So you don't really need separately to write first property at all. You need only second and third property to check. In reality, the easiest test is the first one. Just see if 0 is there or not. Okay, this is easy to check, and this is why I'm just bringing that as a separate property. It's just very easy to say that this is not subspace if it is not there. Okay, so this is more for filtering out not subspaces. But you don't need the first property, really. Third one includes the first one. Any questions on that? Okay, who can read that? Now we are getting to that, getting used to math, you know, getting used to notation, getting used to linear algebra stuff and scientific papers, how people write stuff. Who can read what? I mean, this is not for grade, okay? Don't worry. You can make mistakes, that's fine.
Let me try.
Okay.
W is a subset of V if all elements of X and Y belongs to W, and alpha and beta belongs to the set of complex numbers, such that the product of alpha and X plus beta and Y belongs to W.
Yes. Okay, this is correct. So the overall idea, people learn that in engineering is superposition typically. That you can add multiple inputs and outputs, and then the outputs are also added or multiplied by the same scalars. This is linearity property. Okay, combines into linearity property. So instead of separating addition and multiplication by scalar, this property puts both of them together as a single rule. So you can say that if addition is closed and multiplication by scalar is closed, it's if and only if alpha times x plus beta times y is closed operation. right? This is equivalent to the previous one. And then W, then subset of V, okay, which means subspace in that case, all right? Here's example of subspace. Triangular matrices are subspace of all matrices because some of the triangular matrices still triangular matrices of the same kind, right? If you multiply by constant triangular matrix, still will be triangular matrix of the same kind. Zeros will not become something else, okay, in that matrix, in the other triangle. So this is subspace of space of all matrices. And you have many other examples of that kind. And obviously zero matrix is also triangular. Okay, so. Well, this is the peak of that lecture in general, most difficult slides. And we will get to that diagram on the right, which summarizes probably half of the linear algebra course in one picture. And I love that kind of graphical representation for almost everything you need to know about spaces. And again, I'm not expecting you to understand all of the details of like what goes where and how, and we will get back to the diagram a few times in that lecture, just to see different connections between vectors and spaces and definitions and what works how. And I modified that from, like I picked that from internet, modified that you have reference to where it is coming from. They have pretty nice lecture also online on all of the subspaces, but here are the things that we need to understand from the things. So first I will give definitions of different spaces that we will be working with. And then I will show connections between all of the subspaces in linear algebra, and it will connect together multiple different topics. I believe that this kind of diagram on the right and conclusions from the diagram on the right was called fundamental theorem of linear algebra. This was coined by Gilbert Strang. Have you heard about Gilbert Strang? He was professor emeritus at MIT, very famous for his online linear algebra lectures, video lectures, which are available still online for his courses. And he taught it for 50 years, whatever. Now he is probably 90, so he is pretty old. And so he's famous for his linear algebra, and it's available on OCW. Are you familiar with OCW from MIT? Open courseware. They just share lectures for all public for free. And he has all of this linear algebra, engineering algebra, optimization, and other linear stuff, okay? A lot of engineering stuff. Very interesting lectures, very exciting stuff. And he's doing also a lot of applications in his lectures related to machine learning and other things. So very recommended to go and see these lectures. Now, so Gil Strang, he coins it as fundamental theorem of linear algebra, all these connections between multiple different subspaces. So what are the subspaces? If you have matrix, which is not necessarily square matrix, but could be rectangular matrix, m by n, all right? And it could be complex or real, it doesn't matter. So I'm writing that complex, but you can imagine that as real matrix as well. You have column space, and column space, sometimes called also range, is subspace of C to the M, which is vector, okay? M elements vector, generated by span of A columns. So linear combination of columns of A, you're taking all of the columns, making linear combination of them with any coefficients alpha 1, 2, 3, 4, 5, you get column subspace, okay? It's called column space of matrix A. Any questions on that? This is how it is defined. Linear combination of columns of A is that same. We will call it, like we will write that as col SPA, that kind of thing. Column space. So it's linear, just linear combination, any linear combination, and you can choose any alpha you want, including zeros. Any linear combination will give you that same, all right? Now, row space obviously is the same thing for rows of matrix A. So if you combine, make a linear combination of rows of A, you get row space, and you will write that as row SPA. row space A, okay? And pay attention that since you have m rows and n columns, right? It's like m by n, the dimensions will be appropriate for the vectors of linear combination. So if your row, like you have column space, each column is length m, so it will be Cm. Each row is length n, so it will be Cn or Rn, right? So it's just generated by the rows or columns of A. So this is simple to remember. Now we're getting into something a little bit more complicated. It's called null space. And many people actually write that as kind of curvy n, like almost like normal distribution type of letter, but we will call it ker. It's other way, kernel. All right, so this will be that kind of thing. Kernel of A. And this is all of the solutions of system of equations AX equals 0. Okay? So if A is invertible, square and invertible, this will be only 0 vector. So this will be very small subspace, okay? Only one vector in that subspace, vector of 0. But if A is not invertible or rectangular, you can have multiple different solutions to that equation, right? You can have infinite number of solutions to that equation, obviously. And all of the solutions will generate also subspace, and the subspace will be called null, like 0 subspace, in a sense, of that matrix A, which means, like, what are the vectors that if you multiply them by A from the left, you will get 0 vector, all right? And this will be also n lengths, because all of the x vectors are length n. Remember, this is the same as dimensions in the number of columns, because we multiply column by that vector x. Any questions on that? So this is null space. All right. And then you have also left null space. So left null space is the same thing for A transpose. Again, you have like rows and columns. Here we're also switching rows and columns by doing transpose. So this is x transpose A equals to 0. So you're multiplying by A, x transpose, which will be a row vector, multiplied by matrix, okay? And this will be your null space. Solutions of that equation will be your null space, all of the possible solutions, all right? So this is how we define these 4 subspaces. Now, geometrically, we can represent them as some sort of rectangles. Obviously, they are not rectangles, but this is just graphical sketch description of how subspaces look like a diagram, all right? So here's how it works. Okay, this is a little bit tricky. Try to follow. So if you have matrix A, which is m by n, and you start with this vector of length n, and you multiply by that vector matrix A from the left, you get another vector which is length m, right? Remember how you work with dimensions. So you practically transforming n's length into m's length. All right, this is what you do when you multiply by matrix A, that vector. Okay, this is what you get. So let's say you have that vector x, which is somewhere in space, wherever it is, okay? And this arrow shows you that if you multiply by A, you get some vector B, which will be here, okay? Why is that vector B is in column space of A? So you multiply, you're taking some element x, which is just some point in n-dimensional space, whatever it is. You multiply it by matrix A, you get in some vector B, whatever it is, okay? And this vector, let's say, is somewhere here, wherever the point is. But I'm claiming that this point should be in column space of A, which means it could be represented as linear combination of columns of A. Why is that? You saw that before. This is hint.
Because B is formed by just it's formed by multiplying the vectors in A and just adding them. So it will definitely be in the linear combination of A.
So if you remember, we talked about 2 ways of multiplying matrix by a vector. One way, you're multiplying rows by columns, which means like element by element, and then dot product of rows and columns. And second way, which we discussed, is that you're taking each one of them and multiplying by column, then second one by second column, plus third one by third column, and adding the columns. But what is that? This is exactly linear combination of columns. So you're taking vector x, which is like x1, 2, 3, 4, 5. So it's x1 is your alpha 1 times first column, plus x2 times second column, plus this is exactly what AB means, AX means, right? This is multiplication of matrix by a vector, which means that if you're taking coefficients alpha 1 through n as x1 through n, this is linear combination of columns of matrix A, which means if you multiply A by X, you get something in column space of A, which is linear combination of columns of A, by definition of how you multiply matrices by vectors, all right? This is what it means. So this point has to be in the red space here, okay? Now, second thing, you have the row space, which is all of the combinations of rows, linear combinations of rows of matrix A. And you have that kernel of A, which is like what will solve the equation AX equals to 0. Now we can show that they are orthogonal, which means that the vectors in one of them cannot be in the second one at all, okay? And same thing the other way around. And I'm not proving it, but you just need to remember that they're completely orthogonal. This is what that small corner says, like perpendicular to each other. They do not have anything in common. More than that, we can show that they include all of the vectors that you need to have, which means that if some vector is not in null space, it has to be in row space, or other way around. Everything which is in row space, not in null space, everything which is in null space, not in row space. So it's like works both ways, which means that any vector that you take from here, okay, this is your kind of input, any vectors that you can take from here should be here or there. So it should be some sort of combination of some of them that you can represent any vector. So you can say that x equals x from row space, xr, plus x from null space, xn. So you can write that as just sum of these two vectors from here or from there, all right? So this is what these dotted lines mean. Okay, so you can write that one as combination of row space and kernel space. Okay, so if this is the case, and you multiply that by A by X, right, and X is that thing, here is what happens, okay? So you have A times XR plus XN, which is X, but A times XN by definition is 0, right? Because this is null space, okay? So this thing will be AXR, which means that AX equals AXR. So you going from row space to the same thing, to the column space with that vector, when you multiply it by XR. So AXR will be here, second, okay. And then it will move here. Now, same thing you can say about these two. They are orthogonal and they do not include same vectors. If vector is in kernel of A transpose or left null space, it cannot be in column space or vice versa, okay? So they are completely orthogonal, but all of the vectors need to be included in this one or this one, okay? Which means that they are including all of the possible outputs of vectors that you could have from multiplication by matrix A, okay? So this is overall theorem, and obviously that vector from kernel A should be converted into 0 vector, okay? That simple dot here by definition, because AXN equals to 0. What else we can say about that? So we will talk about dimensions a little bit later, so we'll get back to that graph to describe what it means. Any questions on that? So this is kind of interconnection of all the things together in a single picture. Again, I know it's kind of tough to get all of it together, but this is just
I've been struggling to understand specifically the row space. Right?
Which is
The row space.
row space.
Yeah. So for the column space, I am able to kind of geometrically say that if there's a three-dimensional kind of space, and then you pick a point, 3 points, and so I'm able to, but for the row space, I am not able to.
So row space is column space of A transpose. Think about that. You transpose in the matrix, and geometrically this is the same thing. It's just column space of A transpose.
And then the next question is, so if you are multiplying a vector by a matrix, and then there is a solution B, then that vector is definitely sitting in the row space of matrix A.
No, it's sitting in the column space of matrix A. Yeah, so if you take any vector, whatever that vector is, and multiplying by matrix A, it has to sit in column space of matrix A because it's linear combination of columns of A.
This is row space of A.
This is row space. So you still will get it into column space. From any place, you get it into column space of A. Because if you multiply A by any vector, it will be in column space of A.
No, I'm not talking about B, but I'm talking about X itself. If
This is XR. It's not like regular X. It's some set of X's which are sitting in row space of matrix A, which is just rows of A. So if you multiply A by its own row, you will still have linear one of the combinations of columns of A. Okay. So you're taking like pick one row, like second row of matrix A, and this will be your X vector. Okay. So if you're multiplying A by that second row A, okay. So second row will be practically like squared values of all the second row, but others will be something else, right? So you'll get numbers which are M numbers, right? If you multiply by that row, you'll have M numbers. These M numbers will be represented as a combination columns of A. All right? So this is how it works. Yeah, tricky a little bit. A lot of thinking to do here to get there. Yes.
Can you explain again why AX equals to B will be in the column space of A?
So here's how it goes. Any matrix A11, A1, or A, then you have them here, then you have A and N, vector X1, row Xn to measure dimension. So this rectangular matrix of any kind. Okay, and this vector of length n, and you need to have same number of elements here and there, right? So you can write that as A11, AM1 times X1 plus A12, AM2 times X2 plus, and so on. Right? This is how you multiply matrix by vector. At least that way. I mean, you can multiply this one by this one plus this one by the different way, okay? But you can write it also that, and you will get exactly the same multiplication. So you'll get vector, which is A11 times X1, A12 times X2, and so on. So think about Z as alpha. This is alpha 1, this is alpha 2, this is alpha n. So it's alpha 1 x1 plus alpha 2 x2 plus alpha m xn. So what is that? This is linear combination by definition of columns of A. And each one of them is not x.
Well, A1.
We shouldn't use x. We'll call it A columns. Okay. Differentiate from actual x. Okay. So A1 is first column, A2 is the second column, and so on. So it's linear combination of columns of A. Right? So by definition, linear combination of columns of A is column space of A. This is what it is. Okay? This is A times X. So this is B, right? So this is vector B. So B equals linear combination of columns of A. Okay. Other questions? All right, I think we can stop here, and next time we will continue with some applications and a few more definitions. Okay? Thank you.